We are recording very well. So what we do today, we play with a beam that is undergoing transversal vibration. So the idea is that this object is a beam. The idea is that we are making it connected to the ground in locations here just to fix our ideas. And we are studying the vibration into the y-x plane. So we are making so that the beam is vibrating, staying into this plane. Means that the hypothetical axis that is corresponding to the x-axis, this axis that is, let's say, written into the solid beam, is just moving into the plane y-x. And so we will study the coordinate of the axis of the beam that is moving into the y-x plane. And so also next we will show a diagram that will be a diagram like that, and we say that this is the x-axis. This is the y coordinate, function of space-time, and we are studying the movement of each section of the beam that is so the plane of this section, so an hypothetical central axis of the beam that is undergoing this vibration, staying into the x-y axis. In order to be sure that all of that is working, so this is a very practical, very meaningful, of course, but if we go into the little bit, very minor, step into the theory of the beam that I don't want to explain because you already did it, we should recognize that the beam is staying to the three-dimensional world, of course. Therefore, there is also an z-axis. And if we cut the beam and we show the appearance of the beam, now we are reproducing here a typical section of a mechanical beam that we are using to build structures like those. There's plenty of beams around here, very similar to those, to that one. And so the idea is that the y-axis is this one. The x-axis, that is along which we are studying the transversal movement, is the one that is getting out from the point that we are calling G, where G is centroid, that is the center of gravity, but it's not necessary to speak about gravity. It is a geometrical property. So it is of course the center of gravity if we are into the gravitational field, but the property of this point is that the static moment with respect of that point of the area is null. That's it. The static, so the moment of the first order of the area distribution of the section with respect of that point is null. This is the property that you studied into the course of applied mechanics. Okay, anyway, it is the known concept of center of gravity and the centroid or whatever. But then the property that we need to have into the beam for this beam is that if the beam is vibrating, the axis is staying into that plane. So there is somehow a symmetry. And so we study the vibration of this beam that is undergoing vibration along a principal axis of inertia. So we are supposing that the bending of this beam is happening with the neutral axis, that is the z-axis. So we are supposing that all of that is working with an x, y, z system of reference centered into the centroid or center of gravity of the section. And the axis z is the neutral bending axis of the beam. Then we should say, what is a neutral bending axis of the beam? We don't go into those things because are not belonging to our course. So we could just say that the bending vibration is happening so that what is up if the beam is bending going down, like what is shown here, the material that is above the neutral axis undergoing compression, strain, and stress, and the material below the neutral axis is undergoing extension, positive compression and tensioning, stress and strain. All right. So we assume that everything is working like that, and then after having all of that, we will forget that there is this object. We will just make the drawing of the beam, assuming that it is working like that, and having the concept of moment of inertia that we call JZ, that we need to use in order to show the bending properties, and having the idea that the moment of inertia with respect of the neutral axis and over which is happening the bending vibration of the beam is written as the second order moment of the distribution of area with respect of that axis. So we are using the elementary area dA that is associated to a point P, to the location P. P is the location of the point where is this area, and we write we make the mean of the quantity square of the distance multiplied by the area, and we are averaging all over the area of the system. So we are averaging. We are making the addition. We are making the total of this product elementary area times the square of the distance of that area with respect of the neutral axis. What could be considered the average is what we call the axis, but we don't use it. So let's stay on this concept of the moment of inertia with respect of that axis, and because we are using this. Then, as usual, we say that the vibration that we are looking at are small. Small, it means that the problem is linear. So we are working with linear problems. For which reason? Because the problem is linear. What does it mean that the problem is linear? It means that the vibrations are small. So it is, but then finally they are not infinitesimal. We are repeating what we already said. So the theory is mathematical theory is running when everything is when the displacement is infinitesimal, but it is finite. And so let's say that if we have a beam with a length of 10 meters and the bending displacement is 1 centimeter, one divided the length is 10 multiplied by 100 makes 1 divided by 1000. All right, and so so this is small because the deflection is 1000 of the length. All right, and so all the theory of the infinitesimal amplitude of the displacement is working with something like that. So this is the idea. We must have an idea of what is the meaning of this this concept small. So if you have a beam that is undergoing 10 centimeters of displacement with 10 meters of length, this is just 1 over 100, all right? And 1 over 100 is starts being something that is quite relevant in terms of amplitude. Well, but the quantitative way that the very first let's say formula that we are using in order to say that the vibrations are small is to say that the axis of the beam that we are reading, about which we are reading the movement in order to describe the vibration of the beam, is associated to a shape, so to a linear shape, so we are following the shape of this axis. And we are following also the quantitative representation of this shape. In this quantitative representation, we need to know the tangent of this shape. And the idea is that everything is small when the tangent can be confused with the angle. So when the angle in radians, phi, can be considered equal to the tangent. But the tangent, so this is almost equal. And this is equal. So the angle, the tangent is equal to the derivative of the shape of the line, of the y function of x. And so what we say that is that finally the infinitesimal increase of the angle, dc, is the second order derivative of the displacement with respect of the origin of the x coordinate multiplied by dx. This is the fundamental formula that we are using in order to say that dphi over dx, so the derivative of the angle with respect of the along axis coordinate x is the second order derivative of the shape of the line. All right, we are using this formula. All right, well, next we have to build the next formulas. So I make some small drawing and then we make comments on the drawings. All right, we start with this. So we are considering an elementary piece of elementary slice of the beam. So this is the x-axis, this is the x-axis, and this is the y-axis, and the beam is moved, so it's moving into this plane, all right? So we are considering the axial, the internal actions into the beam. So we are considering moment, bending moment, shear, and the axial action, but at the moment we are not considering it. So we are just considering share and moment, all right, in this by now. Then M is the mass per unit length, so kilos over meter is the dimension. M, that could be a function of the location of the space. So we are considering a monodimensional beam. And so, of course, we making the moment with respect of a point like here incremented. So we are considering that the bending moment is a function of the coordinate, of the running coordinate. The bending moment is changing along the beam, and is changing also along the time. So all those quantities are changing both in time and space. And so also the share is changing. And so I am representing in the incremented section, this is the section at the location x, this is the section at the location x plus dx. And so at the incremented location, the quantities are incremented, all right? Making the moment with respect of O, we are saying that the share T multiplied by dx is plus the extra moment is equal to 0. So we are saying T dx plus dm is equal to 0 because this moment and this moment is canceling, all right? And so we are saying that the extra dm is equal plus the tension, the share multiplying dx is giving 0. And so we are saying that T is equal minus dm over dx. In the slides that we are using this convention, and in my opinion, in the exercise of Julia, she's using the opposite convention, but because in my opinion, she's representing the incremented share in the other side. It doesn't make any difference because the final formulas are exactly the same. So we should underline here that in case we have some inertial force, and we have actually an inertial force, because what we are studying one step ahead is the equilibrium of this elementary slice of beam as an effect of the inertial forces. It is not changing what is we are saying. So in case we have here a force that is m multiplied dx second order derivative y time twice multiplied dx. So this is the elementary inertial force because it is an elementary mass m dx. The acceleration, second order derivative of the displacement with respect of time twice, and dx is already here, all right? This is the force. If we are making the moment with respect of this point of all the forces, I have to multiply this extra force times dx divided by 2, because this dx divided by 2 is the distance from of the element of the inertial force from the point at which we are making this, we are writing the moment, all right? So we have this extra contribution. So I should add to this calculation something here that is plus this quantity. That is the contribution of an extra moment, but this contribution has dx power of 2. It is an infinitesimal or of larger magnitude, all right? So here we are speaking about first order infinitesimal. Here, this is the second order infinitesimal. So we have dx multiplied power of 2, okay? And so this is not giving any contribution. So there is a small contribution, but it is negligible because it is associated to dx power of 2 instead of dx power of 1 as it is this quantity, all right? Very well, so this is just to say that the equilibrium that is saying that the share is equal to the derivative of the moment is still rigorous, although we have the inertial forces. All right. Next, the fundamental equation that we are using in order to write the dynamics is a very simple, elementary, absolutely, I don't say stupid thing, but it's a very elementary. So we are just saying that this slice of beam is in equilibrium under the effect of the transversal forces. That's it. It's finished. We are just saying that. And so what we are saying is that the transversal forces that are acting on this element is the shear on the left, the shear on the right, and the inertial force itself. And so what we are saying is that so the equilibrium is the extra, so the increment in the shear is balancing the inertial force. And so dt is equal to mass per unit length multiplying dx multiplying second order derivative acceleration, local acceleration. We write all of that saying that dt is equal to dt over dx multiplied dx. So we are saying that the growth of the shear is the partial derivative of the shear with respect of space multiplied by dx. And so we write, this is the fundamental equation that we are writing. Next, we have to add other concepts in order to write the full thing. So wait 1 second, I make the drawing of what we need next. All right. I use this drawing in order to say that, let's make it more realistic. This is the elementary slice of beam that is inclined at the section X of an angle that is phi. So at the location X, the slice of beam is inclined of a quantity phi. If I am looking to an incremented location, X plus dx, I recognize, so at the location X plus dx, so this is X plus dx, I recognize that I have an incremented. So the angle is phi plus d phi. The increment into the angle of the section is the measure of the bending moment, scaled by the geometrical inertial properties, the modulus of elasticity, the moment of inertia with respect of bending of the neutral bending axis, and multiplied by dx. So the incremental angle is proportional to how much I'm moving, dx, through the bending moment. So the incremental incremental rotation of the section is measuring the bending moment. And we write all of that saying that we write the bending moment equal to Ej multiplied the partial derivative of the deflection with respect of the axial coordinate. And so we write that given that we are allowed to say that the derivative of the angular location of the section is the second order derivative of the shape of the axis, because we are working with the small displacement. So this is the fundamental hypothesis. So this is depending on the linearity of the problem. So if the problem is undergoing very large displacement, this is no more true. All right? Well, so now we substitute, instead of this, we write that, and then we go back to the fundamental equation. The fundamental equation is the equilibrium. So remember that we are just writing the transversal equilibrium of the beam. That's it. So this is what we are writing. So we are saying that the elementary slice of the beam is in equilibrium. In equilibrium among the shear and the inertial forces. And so we write that the elementary inertial force, m, second order derivative with respect of time, is the derivative of the shear. Derivative, and here is the shear, but the shear is, where is it? The shear is minus the derivative of the moment. And so I say minus the derivative of something. What is this something? The moment. Who is the moment? Is this object here. Finished. We are finished. And so this is the partial derivative equation. This is the P, D, E of the beam undergoing bending vibration into the XY plane. All right, in which way we are using it? So I think that it is interesting, and so I keep it. I think that it is interesting to write everything without the simplification hypothesis, unless the hypothesis of being the displacement small. And so the simplification hypotheses that are coming into now that we didn't use in order to write the PDE. So we didn't use any simplification unless this one, unless the Euler-Bernoulli representation of the structural behavior of the beam. So we used the Euler-Bernoulli representation, so it is this one. So this is coming from the Euler-Bernoulli theory of the bending beam. The incremental angular collocation of a section is associated to a bending moment, the bending moment scaled by the geometrical inertial properties. So this is the theory of the Euler-Bernoulli beam that we are using. And no other simplification. So the fundamental simplification is that the displacements are small. But now what we can say, we make a very important simplification that is helping to have the possibility to do something. Otherwise, we are stopped here. We don't go ahead. We use the hypothesis that the quantity are uniform. So we say that m x is constant and ej x is constant, okay? And so we forget, we cancel x. And so at this point, what we write is second order derivative y times twice is equal to ej gets out of the derivatives, m goes in this side. This is, sorry, there is a minus that is wrong. No, it's okay, it's okay. So there is this minus here. And so we bring in the other side without the minus, all of that, all right? We divide Ej times mass per unit length. Okay, so under the hypothesis that everything is constant, is not dependent on x, so mass per unit length constant and inertial properties constant, all right, all of that goes together. M goes here below the fraction line, and so I write second order derivative with respect of time, minus goes first, goes on the left, plus Ejz divided by m, and so I'm doing the one order of derivative more, one order of the derivative more. This is 2, 3, 4, and this is the partial derivative equation. And this is what the word we are working with is speaking this language. All right. we are very confident that what we already made with the equation of waves of the tensional cable is working also here. And so we try to see if it works. And so we are confident that a possible solution of this partial differential equation is simply a separate variable representation of this space-time representation of the deflection. And in order to be written in this way. If we are using this representation, if we are using this hypothesis into here, now in order not to spend 2 hours doing simple calculation, we have to remind what we did. Let's try to remind what we did with the separate variable. So taking the partial derivative with respect of time, we are not acting on the function of space. We are just taking we are writing G2 dots, all right? The function is y. The function y is the product of G times phi. The partial derivative of that object is active on the function, making G, function of time, transformed in G2 dots. It means second order derivative of the function G. The function phi is staying like a constant, all right? When I do the fourth order derivative with respect of space, it is exactly the same. The function G is not undergoing any change, it's staying like a constant, and I am applying the fourth order derivative to the function phi, and I will represent it like phi first for the first derivative, second, third, fourth for the fourth derivative. Of course, this will be phi fourth multiplied by G. This is G2 dots multiplied by phi, all right? Everything is still mixed. In order not to make everything mixed, I divide everything by G times phi, okay? So, and we do this. And so this is exactly the same thing that we did. And so we write G2 dots phi plus E J Z divided M. And here I write G, let's use G phi fourth, all right? Now we remind that this is function of time, this is function of space, this is function of time, this is function of space, all right? All right? What I do? I divide everything 1 divided G times phi, all right? But I have to say that this is equal 0. I divide everything G times phi, okay? Dividing everything times the product, G times phi, is happening that phi is canceling this phi, and what is left is G. And so I divide this object times this object. Phi is cancelled, and what is left is G2 dot divided by G plus E, J, Z divided M. And here is the same. G is cancelled, and what is left is phi, multiplied phi fourth divided by phi. And so now I remember that what a strange thing. G is function of time, phi is function of space, and we are saying that I write here equal minus, so everything was equal to 0, and so I write that this is equal to that with the minus ahead. And so I'm saying that a function of time is equal to a function of space. This is very unexpected how it works. It is possible, it is not possible, yes, it is possible, just in case this object is a constant, the same constant that is this object here. And so I write here minus omega 0 square. For which reason? I write G minus omega 0 square, because G two dots divided G equal minus omega 0 square is coming from the equation G two dots plus omega 0 square G equals 0. Okay, second order derivative, second order ordinary differential equation. That is the equation of the fundamental equation of the vibration that are saying that in case it is written like that, with this quantity, a positive quantity, omega 0 square is a real number, power of 2 that is a positive number, yes, this is a vibration. This is a representative of a vibration that is constant in magnitude, all right, at a circular frequency omega 0, all right? Well, for which reason I'm forcing the problem to be like that? Because I could say it is a constant, but not a negative, it's positive. Why not positive? Because if it was positive, here I should have had a minus. This minus means that the roots of this equation are not the imaginary roots, but are real roots. And so instead of having a behavior like that, I should have had a behavior that is or an exponential collapsing behavior like this, or also this one. So this is divergent. Divergent means that the system is undergoing infinity energy, okay? For which reason this the bending beam that is vibrating positioned over a table is undergoing infinity energy. It is not possible. So it is not physical. It is not applicable. So the solution with the positive number here is not applicable. So we have to select that among the different mathematical possible solution, this possible mathematical solution of a divergent behavior of the system is not applicable to the case that we are studying. So we are forgetting. And it will come back soon. It will come back soon in a situation where instead we will use a positive number here. It will happen, can happen, not now. Not now, because we are studying a problem in which the energy is limited. All right, well, so we know that, and so we know that we can go ahead saying that we have to study the function So the key point now is to name the quantity omega 0 square m divided ej with a new name. We call it gamma square, gamma fourth, gamma power of 4. Okay? We name this quantity like that. Why we can do that? Because m is larger than 0, e is larger than 0, jz is larger than 0. So the quantity mass E, J are both, all of them larger than 0, so omega 0 squared times this quantity is a positive quantity, being gamma, real number. We call gamma real number larger than 0. All right. And we write the equation. All right, so I made the passage here. Lambda 4 minus gamma 4, phi 0, and so on. So the equation is lambda 4 equal gamma 4. Lambda square. Okay, so we are just naming this quantity. Okay, then we come back to the mechanical quantity. By now we are just using gamma. Okay, and so gamma lambda 4 equal gamma 4. It means that lambda square it is equal plus minus gamma square, and so the 4 roots are the 2 imaginary numbers I gamma plus minus, and the 2 real numbers plus minus gamma. So that finally the solution is I want to use the same. So we have the equation, this equation. So this equation gives, of course, the solution, the oscillatory solution, sinus, sine, cosinus, omega 0t, that could also be written as we use the space. So we could write as the addition of sinus plus cosinus or just cosinus with a phase. And the space function is written in this way. We have the imaginary here, the imaginary here. We want to have a real solution. In order to have a real solution, what is needed is that the complex number C2 is equal C1 star. So we need that the two complex quantities here are complex conjugate in order that the addition of this quantity plus this quantity is just giving a sinusoidal and a cosinusoidal. So it's giving a quantity that is associated to the projection over the x-axis of two rotating vectors. The rotating vector that is rotating in a positive direction with angular velocity gamma, the rotating vector that is rotating in the reverse negative direction with the angular velocity minus gamma, and the two of them scaled by complex constant that are so this quantity that is rotating vector, this quantity the rotating vector is multiplied by a constant C1, and all of that is making this object rotating like that, and the other one is making rotating like that. So this is the EI gamma XX. This is E minus I gamma X. So one rotating this way, the second one rotating this way. We are scaling it times a constant, the complex conjugate, and so we have two rotating vectors that are canceling the imaginary part. So this is the imaginary, this is the real. It is always the same story that we are repeating many times. All right, and so we can write this and that are cosinus and sinus, and so we can write the solution in a slightly different way. That is the way that we are using. And now we can cancel all of that. Now, what is happening here is that two new functions are born, the hyperbolic cosinus and the hyperbolic sinus. For which reason? So what is disappeared? Is disappeared C3 and C4. So this object here that was very regular, very simple. So an exponential function of x and function of minus x, then is modified. For which reason is modified? Because it is not convenient to stay with this. It is convenient to use something that is a linear combination of those that are not saying different things, but just adjusted in a different way through the function hyperbolic sinus and hyperbolic cosinus. So and we derive here what we mean by hyperbolic cosinus. So we should know it, but instead we are repeating the hyperbolic cosinus goes like that. This is 0, this is 1. So this is the function hyperbolic cosinus of gamma x. This instead is the function hyperbolic sinus of gamma x goes like that. It is antisymmetrical. This is x and this is 0. Okay. In order to move from this representation to that representation, and so you see that this one becomes antisymmetrical, because if I put a minus into here, I have, it is reversed. All right. In order to move from this representation to the other representation, we write D3 equal. I write it so you check, but so what I mean that if you substitute, if you write the equation using the variables D3 and D4 instead of C3 and C4, and you substitute to the C3 the quantity that is named D3, D4. So we are making a linear combination of the two. So we are using D3 and D4 instead of C3 and C4. It is the same. We can use one of the other because there is the relationship that is linking. So if you're substituting instead of C3 and C4 this quantity into there, you are writing something in which you can recognize this quantity, and it is simplified, and you are naming this quantity hyperbolic cosinus, you are naming this quantity hyperbolic sinus, and then you work with those instead, or you work with those, let's say, synthetic function instead of the elementary function, because they have a behavior that is symmetrical, that is intuitive, that helps to look at the physical representation of the problem. Okay, it is totally the same, but we are using the hyperbolic cosinus, hyperbolic sinus. Maybe I hope that no one of you didn't know that it's possible to do all of that. I wrote for the people who maybe never encountered this substitution. So now I'm canceling because I have to use the blackboard, and we are just keeping the image of in mind. We are keeping in mind the image of the hyperbolic sinus and the hyperbolic cosinus. All right, and finally, we say that y function of x time is equal to g dt multiplying phi dx, where this is phi and where g function of time is a constant multiplying all right. Now, this is the general solution. This is a general solution, time and space, that is satisfying the partial differential equation. At the moment, it is just one of a very general but possible solution of the partial differential equation. Now we have to make it working on something practical. And so in order to make it work on something practical, we try to understand what is happening in case we are representing the behavior. So we want to represent the vibration behavior of a beam, fully constrained in one side, undergoing. But let's say that I make the drawing in the other side in order to write here the equation. So. Okay. So what we do, we play with the boundary condition in order to write the free motion. So this object that we are writing here is the equation, are the function that are representative of the free motion of the system. Now, in order to make it act, to make it work with the actual boundary condition of the system, we have to impose the boundary condition. And so we have to find out which are the boundary conditions. At the location 0, it is null the displacement and null the first derivative. At the location L, it is null the shear and null the moment. All right, finished. And so we have to write it. So we write it. I write the first equation, but then we move to write the matrix. Okay, the first equation is writing that whatever is time, whatever is due in time, the function phi is equal to 0. Position. I hope that it is intuitive for you that very similar is the equation of the first derivative. Very similar is the equation of the second derivative. Very similar is the equation of the third derivative. It is just necessary to write all of that. And what we are recognizing that we are building a system of coefficients that is cosinus 0, sinus 0, hyperbolic cosinus 0, hyperbolic sinus 0, multiplying the unknowns, d1, d2, d3, d4, okay? And so we are writing always the same usual problem where we have a matrix, and here we have cosinus 0, that is 1. Sinus 0, that is 0. Hyperbolic cosinus 0, that is what? 1. Fantastic. that is 1. Hyperbolic sinus 0, that is 0. Perfect. This is our matrix, and here we are positioning the vector d1, d2, d3, d4, all right? Well, equal null. And now, and then the first derivative is minus, we do it by memory. First derivative, cosinus becomes minus sinus. Sinus calculated at 0 is 0. Sinus becomes cosinus. Calculated at 0 is 1. Hyperbolic cosinus. What is interesting of those functions that are the hyperbolic sinus and cosinus. For which reason? Because they behave the same. If you take the derivative of the hyperbolic cosinus, you get the hyperbolic sinus. And if you take the derivative of the hyperbolic sinus, you get the cosinus. Finished. This is the fundamental reason for which we are using it. And so, first order derivative, hyperbolic cosinus becomes sinus at 0, it is 0. Hyperbolic sinus becomes cosinus at 0 is 1. Well, second order derivative, the moment null. Moment null at the free extremity. Moment null is, so second order, so this is cosinus, it becomes minus cosinus, and so we have minus cosinus gamma L. Sinus minus sinus gamma L, di3 cosinus twice gamma L, okay. You should have, what was wrong before? There is a mistake, 2 mistakes. There are 2 mistakes, hidden, a little bit hidden. The derivative is done with respect of who? X. Where is gamma? Gamma. All right. Gamma is here. Outside, because it is the common factor of everything. So, partial derivative with respect of x. Gamma, getting out gamma, gamma, gamma. We have gamma out of here. Okay. Second order derivative, gamma square. We can divide by gamma, yes, because 0 divided by gamma makes 0. Okay? We can do it. In case we have the forced problem, that is what you have in the cable with the 2 domains. The problem we did last time is written for the forced condition with a matrix that is exactly the same. A vector that is the same at the other side, there is a vector that is null everywhere instead for the last element that is the force, because the equilibrium at the connection of the 2 cables, instead of having a 0 force, there is a force that is not null. And so the last 0 of the vector on the right side of the problem last time, the last position is the force acting in the middle. That is null in case of the free motion. It is not null in case of the forced motion. All right? And so if there is a situation like that, as I have to position something known down here, I cannot cancel this gamma force that I should have been here, but I have to take care of that somewhere. All right? All right? So please, let's connect the things together. So some of you is not comfortable, I'm sure, that I am jumping from this problem to the problem that we did last time. All right? But we are speaking about exactly the same thing. Exactly the same equation. We must be aware of what we are doing. All right? What we are doing now here is exactly the same that we did last time. And so we have to jump into what we did last time, looking at the connections. All right, so a moment, it is gamma, second order derivative. share is the third order derivative, minus cosinus becomes sinus, gamma L, gamma 3 times, minus sinus minus cosinus gamma L, CH SH gamma L, CH gamma L. Okay, so we have to repeat what we said the last time. In order to have a solution that is not trivial solution, the trivial solution is, in order to have here 0, 0, 0, 0, so this is the trivial solution, it's very simple. D1, 0, D2, 0, D3, 0, D4, 0. In order not to have the trivial solution as the only one solution, we must have null determinant into here at the purpose of saying that one of those equations is the linear combination of the other. In this situation, it is not possible to give a unique solution, but in an infinity number of solutions, all of them scaled by one factor, okay? And so in order to make the solution, we give to one of those numbers the value of 1, for example, the first, and to the other, it will be d2 divided by d1, d3 divided by d1, d4 divided by d1. And so we are representing the shape of the solution, not the actual value, because the actual value will depend on the initial condition that we are giving to this motion. Okay? All right. So we can all right. Well, so the problem is we are writing so we are requesting, so we write that this object, we name all of that as h function of gamma, all right? We are recognizing that there is gamma into here, but keep in mind that, yes, we have gamma, but gamma means omega, all right? So now it is helpful to stay with gamma and not to substitute with omega, but they are linked. The last time we wanted to stay with omega because it was driving omega. Here, who is driving is gamma, but the two things are linked, and so we must have in mind that it is exactly the same to say that we are saying h function of omega 0, the vector d equal 0, all right? That is saying determinant h omega 0 equal 0, all right? So we are not dismounting what we did the last time. The last time was more useful to stay into, so I wanted the last time to say we are searching the natural frequencies. Here is the same. We are searching the natural frequencies. We are searching the modes of vibration, yes, but it is much more simple here to stay with gamma, to find out gamma, and then from gamma to go into the value of omega, right? So this is clear, yes, so we cancel that, We are canceling this one. We understand that we can stay with the gamma. It is very peculiar that in using the properties if someone of you is using Mathematica, the symbolic, or you is able to work out the determinant, you can recognize that it's very simple because you have this one, and you have to make the determinant of something that finally it is a number 1 that is multiplying the determinant of this object here. So the way in which it is arranged is making so that it's possible to work out the determinant by hand. It's necessary to remind a little bit what we do. And here what you do, you have square cosinus hyperbolic minus square sinus. And there is a property like the property that is in the trigonometric function square sinus plus square cosinus is equal 1 is exactly the same, but there is minus. So using this property, just use this property and working out the determinant is possible, just using this condition, it's possible to write that the determinant H gamma, determinant is equal, it is a magical situation where it is equal to cosinus gamma hyperbolic cosinus gamma, sorry. So believe me, it is possible to show that all of that becomes an equation. And this equation is an equation in gamma. And so it is possible to say that the solutions are the infinity numerable solution where gamma is the solution of the equation cosinus gamma L times hyperbolic cosinus gamma L is equal -1. This is giving gamma 1, gamma 2, gamma n, All right, so having the first solution, gamma 1, that is making null the determinant, we get the 4 numbers here. Those 4 numbers we know that will be given by 1 here and d4 divided by d1, very similarly here, and all the n solutions. So for each solution, we will have different shapes, all right? It is, in my opinion, interesting to have a guess of which will be the first, the second shape, and it should be interesting that you do it by hand and recognizing that, obviously, the first deformed modal shape of vibration of the system will be the one with the lowest tortuosity, having about a deformed shape like that, all right? It will vibrate in the way that we are used to say that the beams are vibrating. If you have an object like that, it is vibrating like that. Very similar. In case we are looking to the second mode, which will be the shape of the second mode, something similar but more tortuous. All right? And so we have to make the drawing. So if we are asking you something like that, it is necessary to start with the right step. The right step, it means that we are focusing our attention to the first thing you are drawing here. In case you are not drawing something that is going parallel here, but you are driving something that is going like that, this is very wrong. So it is what we are looking at. We are looking at that you are not contradicting the hypothesis with which you wrote the solution. The hypothesis with which you wrote the solution is that if the tangent is null, you must make a drawing with the tangent. I'm saying something very obvious, yes. I'm saying something totally obvious. And you say that we are concerned about minor things, aesthetical aspect of the drawings. Yes, we are concerned about the aesthetical aspects of the drawing. They must be good looking. But more than good looking, they must be correct. They must not be wrong, the drawings, all right? So we are focusing our attention to the way in which you are starting the drawing. Is it clear? So you must making some drawings that are meaningful, all right? And if you have some experience, if you make some exercise in which you are playing with numbers, all of that becomes more simple. So it happened that the second mode of vibration could be something like that, and then it is increasing the tortuosity. All right. So an interesting question would be, in case we have all of those numbers, so we have all the vectors here of the constants. So with those vector of constants, we can say that we will have D1 ith, all right, D2 ith, D3 ith, all right, and so gamma I, Okay. Okay, so we were looking at the ith solution where the 4 numbers here will be normalized to 1 here, but we don't care now. They could also be not normalized. We can do what we want, right? But let's just remind that those D1, 2, 3, 4 i's are numbers now for us, are real numbers, all right? And the overall solution will be the Ci multiplied by Gi added all together, so making the summatory over I going from 1 to infinity of Gi multiplied Phi, all right? You wrote something, or Gn, so if the index that is running is, instead of I is n, will be Gn, Phi n, and instead of I will be n, whatever you want, all right? So you make this summatory of space function multiplying time function. In order to make this summatory of objects equal to the initial condition, and the initial condition could be always a location, a collocation of the problem with an initial position and not a null initial position and a velocity. Could be a null velocity, something like that. The same way in which you solved the problem of the tensioned beam. So the point could be that we are saying that at the instant, the zero at the 0 time, we are writing that y x t equals 0 equal f0 function of x and f1 and y dot x t equal 0 equal f2x. So we have an initial condition that is saying displacement at null time, velocity at null time. Maybe the velocity could be this equal. So we are giving the deformed condition, and then we are pulling it, and then we are cutting, and it starts vibrating. So this can be done very quick, very easily. So we are giving a position, and then we make it free. So in which way we make so that those numbers in the summatory from I to 1 to infinity are copying this shape. This problem is not trivial. So for the tensioned cable, what happened is that you used the representation in terms of Fourier series of the deformed shape. So it helped that you recognized into this summatory of cosinus and sinus the possibility to write the initial deformed shape as the representation in Fourier series of that shape. Here is not exactly the same because it is the same up to here. But from here ahead, it's not true. We cannot write, we cannot use the same methodology that we used the previous time. All right, is it clear? At least some of you are following me about what I'm saying. So did someone had, before I mentioned that was already jumped into the point of saying, but what we do that here we have the hyperbolic cosinus, parabolic sinus in order to satisfy the initial condition. In which way we are, because what should we do? We should calculate the value of the scaling of each of them. So we have those that are becoming numbers, but then are scaled by the time function that is giving a scale to this shape through the quantity Ci. So we are scaling big or small, and we are giving a phase. So we are saying this mode of vibration is vibrating with an amplitude and with a phase. All right? I would like that you are starting thinking that if we have the first mode of vibration, and the first mode of vibration is going like that, and the second mode of vibration is going like that, the initial condition will be a situation where we are saying to the first mode of vibration, stay quiet, maybe 0 here, maybe. Or you are the only one and all the other will be cancelled. So we are giving to the initial, through the initial condition, the scale to the modal shape in order that they will run all together in order to make at the initial condition the starting point, all right? I would like that you have this feeling. So we have those quantities that are numbers defining a shape, but this shape then is how do you say, modulated by the time function that is giving them into the modulation, the amplitude, it is large or small, the contribution, and it is giving also the phase. And so we need those numbers, this number and this number for all the modes. So we need to, in order to give the initial condition, we need to say which is the contribution of each mode, and all those modes will continue to vibrate without any damping because there is no hypothesis of damping. And so we are giving an initial condition. These initial conditions are giving those quantities, this quantity and that quantity for all the modes. And then we are turning on the time and they are vibrating. They are vibrating, they are going ahead, and each of them, the mode 1 is running with a frequency that is omega 01, the mode 2 with omega 02, mode 3 omega 03, and whatever. And so the final behavior will be the superposition of all of those that are playing together. All right. But in which way we are calculating this and that? In my opinion, you should not have any answer, and the answer is a bit difficult. We could leave the problem like that. But there is an answer. But for giving the answer, it is necessary to have a concept that is coming later. And the concept that is coming later is that the property that you used for the Fourier transform, that in order to calculate the coefficient is the orthogonality property. The orthogonality property means that if you have this shape and if you have this shape, you make the integral of this times that, you are adding, and the result is null. The orthogonality means that if you are making the cross product of the two modal shapes, in case the modal shapes are sinusoidal like that, the orthogonality, the geometrical orthogonality property is making so that this quantity, this integral is null. This was the property that you used in order to get the coefficient of the Fourier series. So the orthogonality property is that property. But an extension of this property, So what you know now about the orthogonality property is just a geometrical description. This shape times these set shapes integrated all together, one times the other makes a null integral over the period. And you have this strong idea of the orthogonality property as a geometrical property. The modes of vibration of a structure that is undergoing vibrations and who has a mass distribution are adding a more general, are working in a space that is a bit more general. So we will recognize that this orthogonality property is not just geometrical, is more linked to the property of the structure. And so we will use this orthogonality property that is, we are keeping an orthogonality property, although the shapes are not sinus and cosinus. So also considering shapes that are different, not just sinus and cosinus, we are keeping, is still alive. There is a very general permanence of this orthogonality property. And so in order to calculate those quantities, we will use the orthogonality property that now we are not knowing. In order to know the orthogonality property, it is necessary to speak about decomposition into principal coordinates and modal approach, this kind of things. All right, and but I hope that you are keeping alive your attention on this problem of giving the initial condition. Now I give you to do the exercise of making something that is extremely simple, that is X. So this is the same beam that we had before, but it is simply supported at the constraints, and so it is the same problem, absolutely the same problem. We write the 4 equation, we write directly the matrix, we write D1, D2, D3, D4 equal 0. And then we are feeding the matrix with what? With displacement null at the location 0. Displacement null at the location 0 is 1, is 0, 1, cosinus 1, no, we write cosinus, sinus 1, 0, 1, 0. Then the second property is moment null at this location. And so this property is a second order derivative with respect of space equals 0. Okay? Moment null here. And so the second order derivative will be that here we have minus 1, cosinus becomes minus cosinus if you make the derivative twice, minus 1, 0. So we have cosinus, sinus, 2 times the derivative, minus sinus, minus cosinus, right? But here, look at that. We have cosinus. The derivative of the hyperbolic cosinus is sinus. The derivative of the sinus is cosinus. There is not the minus that is running. In the derivative of the hyperbolics, we don't switch. The derivative of the sinus is cosinus. Cosinus is sinus. There is not the jump of the switch of the sign. And so this 1 stay 1, and this 0 stay 0. Okay? We are speaking about properties that are properties that some good student of the if there was here some good student of a high school, would say, for which reason we should go to the university to look at those sentences about this quantity that are already known by us. All right? So we must know it. We must know those properties. And so this is 1, this is 0. And this is multiplying D1. So this one is multiplying D1, and this one is multiplying D3, all right? This equation is saying D1 plus D3 equals 0. D1 plus D3 equals 0. This second equation is saying minus D1 plus D3 equals 0. Minus D1 plus D3 equals 0. All right? It is not necessary that I go, I will go ahead here, but by now I have enough for saying that D1 is 0 and D3 is 0, because if I am subtracting, if I am adding the two equations, I am writing 0 plus 2D3 equal 0. That means D3 equal 0. That means D1 equal 0. All right? Is it clear? Very simple thing. So I'm doing quick because I reminded, so before coming here, I was reading the slides, but it is absolutely obvious thing. We are speaking about obvious things. All right? So, because of those constraints, because of this constraint here at the location 0, D1 is null, D3 is null. What is left is the solution in sinus and the solution in parabolic sinus. So I leave to you calculation of the extra, what is going on. What is going on is that we have to write that at the location L, the displacement is null, and at the location L, the second order derivative is null, all right? So we are repeating exactly those two equations, but with the argument L instead of 0, okay? And so it is simple. So we are writing exactly the same thing, sinus and whatever. In doing that, the two equations that you write will be sinus gamma L. So what is left is sinus gamma L, okay? Hyperbolic sinus gamma L, second order derivative minus sinus gamma L, hyperbolic sinus gamma L. Determinant equals 0. So I wrote the problem now is collapsing into the rank 2. The unknown are D2 and D4. All right, we do like that. And so the determinant is, and the determinant is sinus gamma L, hyperbolic sinus gamma L, plus multiplied twice. So the solution of this determinant is twice the product. So this determinant is equal to the hyperbolic sinus is null just when the argument is 0. So it is never null here. So the only way to have null this determinant is that who is null is sinus gamma L. And the solution in order to have sinus gamma L null is gamma L equal n pi. That is exactly the same solution that we had for the tensional cable. That is giving the obvious solution that this beam will vibrate like that with the first modal shape that is made like that, and with the second modal shape that is doing something like that. All right. Gamma L equal n pi means that we are writing sinus 2 pi x divided L divided n. Be like that. So we are writing exactly the same solution that is the one that is running for the tensional cable. So I leave to you to go ahead with this exercise. This exercise is exactly the same exercise of the cable with the overhead that the two coefficients C1 and C3 are null because of the first two equations. What is necessary that you do is to work with numbers to understand what is happening to the frequency in the slide and to recognize that when omega as gamma and omega are not linear together. Omega goes with the square of gamma. Gamma is running linear with the order of the mode, all right? And so the modes will be the first mode, the second mode, exactly as in the tensional cable. And so the wavelength will become smaller, so will become 1/2, 1/3, 1/4, and whatever, like in the tensional cable. But the frequencies will go with the power of 2. So the second mode frequency will be 4 times the first mode frequency. The third mode frequency will be 3 power of 2, 9 times. So the behavior of the beam is very similar, simply supported, but very different because the frequencies are jumping up with the power of 2, and in the cable they are linear with the order of the mode. We have to stop here because the time is finished, but so there is an example into the summary slides that I published. If I'm not wrong, the final two figures are those. Someone of you are recognizing? No. Davvero? Davvero? I check, but because in the very summary, there are two cases that are similar, so I'm comparing a cable and a mass, a cable and a beam having the same mass per unit length, having similar properties in order to have the same natural frequency, all right? So I'm comparing the two cases. So we will make comments. I check why they were not uploaded. All right, I stopped the registration here, and 1 second. I stop.